is A is true now and at all future time steps. So a relatively weakly expressive temporal logic, but we can express this in our sequent calculus by adding three rules. For the next operator, we simply add what's called the necessitation rule. If we have derived gamma delta, we can derive that next gamma, next delta. And I should say next gamma is the set of, is applying the next operator to all elements of gamma. We can put the next operator in front of the formulas in gamma and the formulas in delta, and this is sound. For the field circle, for the always operator, we give a left and a right rule. So the right rule for circle, for always, is that if we have derived that A holds now, and at the next step, from the next time step, A always holds, then this is the same as saying A always holds now. And for the left rule, it's essentially saying the same thing, that A always holding is the same as A holding now, and at the next step, A always holding from then. And these rules actually suffice to allow us to do proof search in the same way we did for classical propositional logic. If a sequent is valid with respect to this interpretation of the temporal operator, then there is a proof. And rather than going through the argument, the general argument, here is I've given one example. So let us do a proof search of always A implies always at the next time step A. Well, we apply the left always rule. I will mark the principal formula. So the left always rule backwards, we get the sequent above. Then we apply the right always rule backwards. And now we get to a sequent where we've got this A, but otherwise we've just got the next operator. What we're going to do is discard the formula A and open up the next operator. We get always A implies A. In order to do this, we open up the left always rule, and now we get the identity sequent when we discard one of the formulas on the left. And on the right-hand branch, it's quite similar. So we discard that A. We will actually discard the formula A as well on the right, and we'll just use undo the next operator. But now we get to something. Our proof search has got us to a sequent which we have already arrived at before. So our proof search here is circular. And this doesn't actually matter, because if we look into the semantics of this proof search, we will see that this is actually making progress in verification. So what we do is, in our proof search, we continue. We've reached the same sequent. Well, we just will start the process again. And what we'll get is some infinite derivation in the right side. Did I write what I wanted to? No. Okay, so let's talk a bit about this first. So we've got this proof search tree. What we want to say is that either we find a proof or we show that the end sequent is not valid. And we haven't said what kind of proof we should allow. And it turns out that for this calculus, we want to allow certain ill-founded proofs, i.e. derivations that are infinite trees, some of them, but not all of them. We won't go into the details of the next definition, but here we will define what are the right proofs for us. So we want a notion of trace, following a formula through its breakdown through a branch of the derivation. So in this example, I've taken the part of the proof on the previous slide, and if we follow the formula on the left, we can follow it in this way, and we are following this formula as it's broken down. There are other routes we could pick, and so this is a trace on the left, and if we follow this formula on the right, we see that it proceeds in this way, and this is another trace. So this is the green trace and the red trace. We have a trace on the left side of this branch and a trace on the right side of this branch. And now we say that a trace is good if it's on the right and it goes through a principal occurrence of the always rule infinitely often. Just a technical definition, but it turns out that it's the right one when we say that a proof, an ill-founded proof, is a derivation in which every infinite branch carries a good trace. Now, there are certain special kinds of infinite proofs. The periodic ones, the ones like in our proof sets, which when we repeat a sequence, we start just looping on ourselves. And these are what are called cyclic proofs. So we have cyclic proofs, which are ill-founded proofs, but periodic ones, and we have ill-founded proofs in general. So, yes, so now we've got the soundness and completeness. So ill-founded proofs are sound and complete for linear temporal logic. So the soundness, well, I leave that as an exercise for those that want to explore this. And we'll just talk about completeness. What we do is, as before, we do a proof search. We apply the sequent rules that we have backwards, decomposing all formulas. We apply the next rule whenever no other rule is applicable. Either we find an ill-founded proof, or what does it mean not to find an ill-founded proof? It means that we have constructed a derivation which contains an infinite path where there's no good trace. There's no right trace that is principal infinitely often. Now we found an infinite path, whereas for classical propositional logic, we found just a leaf that was bad. But now if we look at that infinite path, it turns out we can take that path and we can turn it into a counter model. And in classical propositional logic, this was just a one-step process. We defined one valuation and showed that model refutes the sequent. But now we turn this whole path into a whole counter model, which is a valuation for now, and a valuation at one time step, and a valuation at two time steps, etc. And then we verified that this valuation refutes the sequent. So the moral is that our strategy for completeness of this sequent calculus has not changed. It has just relaxed the kind of proof object that we are looking for. And we can also talk about the proof theory of this logic, i.e., which of the rules are recursively admissible. So there's a typo here. I've written the rules of LTL are recursively admissible. I meant the same statement as before. I mean, the rules of LTL are obviously recursively admissible, but their inversions are also recursively admissible. And the proof of this fact proceeds just as before. We have a local transformation of derivations, and what happens once we've done the derivation, this transformation through the whole derivation? Well, we have to verify that we have a proof. Well, let's look at the case of cut, and we will see that second step in the argument a little more detailed. So the claim is the cut rule is recursively admissible in LTL. What we do, we have our transformations from classical propositional logic. We now add new transformations to deal with the new rules we have in the calculus. And those are the rules for next and the left and right always operator. Well, if we have a cut and we've got the cut rule, the cut is formula is an always formula and it is principal, then we are in the situation on the left, and we can write down a transformation for this. We take the three premises, as it were, and it turns out we can cut them against one another. In fact, the strategy looks very similar to the conjunction rule. We turn one cut into two cuts. What we have done is consumed parts of the premises. And the reduction rule for the next operator is actually very similar. There's a difference here, though. In the case of our conjunction reduction, we turned a cut on a conjunction into a cut on conjuncts. So we had a cut formula that was more complex before the transformation than after. But here we have a cut formula on a more complex formula than we started with. So we can't apply an induction hypothesis to this cut, at least not directly. But that's not the point of this recursive transformation. The recursive transformation is simply specify locally what changes you're going to do to the proof, and then just repeat those changes over and over again until you get rid of the cut rule from the derivation. And that is what we'll do. We now look at this cut on the top here, and we don't care what the cut formula is. We ask, can we apply these local transformations to it? And we can. We're always in a position where we can apply one of the transformations we will have defined. So step 1, we add these reductions. Step 2, we apply continuous cut elimination. And this is as before. Step 3 is now something new. Verify preservation of proofhood. Now we have derivations containing cut mapped to derivations containing cut. If we started with an ill-founded proof, we want to know that we get an ill-founded proof at the end. And this is a process that we proceed by induction on the formula rank. So in the inductive way, we do both the verification, or we do both the transformation and verification in one step. We apply an induction hypothesis. In the co-inductive way, there are 2 steps. We have a transformation, and then we have to verify afterwards that this is the right kind of object. Well, generally we're going to be looking at objects of this form. We have a cut at the bottom, and if we follow a trace from one of the cut formulas, we will see a point where it becomes principal. And if we follow this further up, might see another point where it is principal, and so on and so forth. And on the other side of the cut, we'll have the same feature. We can follow this cut formula, and at some point it will be principal in the right rule, and then we will branch right, then it will be a principal in the right rule and branch right, and so on. And so we will always have this mirroring that traces on the right hand side from the cut formula mirror traces on the left-hand side from the cut formula. And now we make an observation that after we perform cut elimination, what we're going to do is we're going to still have everything in this right-hand branch, except the cut formula, except the red formulas. And indeed, ultimately, the cut will get rid of the other formulas here. We'll have everything in the right-hand branch except the red formulas. Now, if the right-hand premise is a proof, then that derivation contains a good trace on the right. And we haven't done anything to this good trace. So after cut elimination, the result of this branch, it will be more complex than it was before, but it will still contain this right good trace. In a nutshell, if we started with proofs and performed the cut reduction process, then every branch in the result will carry a good trace, which means that the cut elimination process sends ill-founded proofs to ill-founded proofs. So now let's look at a perhaps more complex and more interesting study, arithmetic. So what we have here is, of course, natural numbers, and we have induction. And it is induction that is, well, that gives the power for arithmetic, gives its that makes the secret proof theory of it very interesting and in many cases difficult. So the language of arithmetic for me is the usual language. We've got variables, we have zero, we have a successor function, we have addition, and we have multiplication. That's the terms, and the formula language, I have equality, I have all the logical operators from classical propositional logic, and I now have a quantifier. I have for all x, a. And I could have exists x, a, but for classical arithmetic, we can define this by negation. So exists x, a is the same as not for all not a, where negation is defined by implication. And now our sequent calculus for arithmetic is we take classical propositional logic and we add new rules for the various new logical and non-logical information. So we want to add rules for equality and terms, and I just present the rules for equality. So we have a right rule for equality, which says that we can always derive the trivial equality, and the left equality rule is a sort of substitution. If we prove something about S, then under the assumption that S equals T, we can prove something about T. And a final rule that is useful in these contexts is the substitution rule. If we have derived a sequent, then we can uniformly substitute in that sequent a term for a variable. But actually, the substitution rule is derivable from the two equality rules. So this is derivable, but we will still use the substitution rule because it has a lot of use as well. And then we will also want rules or initial sequence about the equational theory, so the theory of plus and times, but I will omit those. Next, we want rules for the universal quantifier. I won't mention them here, we'll come back to that shortly, but for now let's imagine somehow we've come up with a left and a right rule for the universal quantifier. The next ingredient for the theory of arithmetic is the induction axiom, which we can just say that as an initial sequence we have the sequence that says if A holds and is closed under successor, then for all x A. And finally, for arithmetic is the rule of cut, we didn't have cut in our classical propositional logic because we didn't need it. But for sequent calculus arithmetic, we do need cut. And that is essentially Gödel's second incompleteness theorem. There are no finitary cut-free calculi for Peano arithmetic. There is some technical work going on to show that you can reduce this as a second incompleteness theorem, but at its heart, it's just the second incompleteness theorem. So this gives us a natural finitary sequent calculus for Peano arithmetic. And if we want to analyze the proof theory of this jig, such finitary calculi are not sufficient, and we need to talk about infinitary proofs in order to get the kind of robust properties that we want. In the context of arithmetic, the common step or the tradition is not to look at ill-founded proofs, but to look at infinitely wide proofs. We use the omega rule. The omega rule is a rule for introducing the universal quantifier. It says that we can introduce the universal quantifier if we have derived each numerical instance of the formula. And now let's use a turnstile for provability in the finitary sequent calculus, and subscript omega for using provability where we have this omega rule. And now the standard proof theoretic analysis of Peano arithmetic, also known as the ordinal analysis, says that if gamma delta has a finite proof in Peano arithmetic, then it has an omega proof, which is cut-free, so we don't need the cut rule anymore, and the height of this proof is bounded by an ordinal epsilon 0. Height has to be in inverted commas because the proof is still infinite, but the point is it's infinitely wide, but it is well founded, so every path is finite, and therefore we can assign an ordinal height to the measuring the proof. And this is known as the ordinal epsilon 0 for the case of Peano arithmetic. Now, there's a caveat with this claim, and that is what I call the paradox of the omega rule. If a sequent gamma delta is valid in the standard model, if it's true in the standard model of arithmetic, then actually we can find a cut-free proof of that sequent whose height is much smaller than epsilon 0. And epsilon 0 is known to be the proof theoretic ordinal of Peano arithmetic to somehow characterize the strength of Peano arithmetic. But actually, there are omega proofs that are much smaller. And the question here is, why is this not a paradox? I mean, why is the ordinal analysis of Peano arithmetic actually a valuable statement? And the reason is because we have to be very careful about what we think of as an omega proof. And the point is that in the ordinal analysis of Peano arithmetic, there is another ingredient which actually rarely gets proper mention. If there's a derivation given a sequent that is provable in Peano arithmetic, then there is an omega proof which is cut-free, has height epsilon 0, but importantly, this proof is recursive. Have to be a little careful about what we mean by recursive when we have infinitely wide proofs, but it can be given a robust definition. And that is the catch. In the case of the paradox, this proof will be not recursive in general. And what is informative about the ordinal analysis of Peano arithmetic is this feature of that we're talking about recursive omega proofs. And therefore, without careful restriction, the notion of working with omega proofs, well, it's uninformative because the complexity of the omega proof, say by its ordinal height, is only relevant when we have certain structural constraints on it, say recursiveness. And indeed, this issue of whether proofs must be recursive or not is often a side note, or it's left implicit in the work. It's also not particularly extensible because omega proofs, they work well for arithmetic. The omega rule is about arithmetic. But how would we take this notion and generalize it to other inductive concepts? So, for example, for the temporal, let's put LTL as a question mark, linear temporal logic. What should an omega proof look like for linear temporal logic? Or theories of general inductive definitions, or more abstractly, co-inductive concepts, inductive concepts, finite trees, infinite trees, theories of streams and sequences. And finally, there's a lot of non-modularity in cut elimination here. So this is always the case for cut elimination, that when it works for one system, that does not mean that it will work for a simple expanding the system by new sequence rules. So if we have to dramatically change the notion of omega proof, then we have to verify cut elimination from scratch. Well, let's take a step back because so far in this talk, I've always been talking in terms of proof search, that is. And what happens if we apply proof search to the case of arithmetic? Now, for certain reasons, it's helpful for us to make a subtle change to the language of arithmetic. And that is that rather than using quantifiers for all x f of x, I'm going to use quantifiers for all x greater than or equal to y f of x. And then I define the usual quantifier as just being, well, for all x greater than or equal to 0 f of x. X's central quantifier is defined by double negation as usual. And now we can write down our two local reduction rules. These are finitary, they're not omega rules. We've got one conclusion, we have two premises. We have the rule on the right, which says that we can introduce one of these quantifiers if we can prove that A holds for y and that A holds for every x at least the successor of y. So A holds, we have for all x greater than or equal to y if A holds for y and A holds for all x strictly greater than y. And the left side is similar. We have, excuse me, to introduce the same quantifier on the left, we want to know that A holds for y and A holds for all things greater than or equal to the successor y. Now with these rules, we can ask us we can look at a proof search of a complex sequence like the induction axiom. If we don't have the induction as an initial sequence, how would it look? What would it look like to proof search it? And so what we're going to be searching for is a proof of the sequence gamma 0 implies for all y a of y, where gamma is the statement that or gamma x is the statement that is the set containing two formulas, a of x and that a is inductive for all numbers larger than at least x. And now we just we do a proof search on it. So what we do, first of all, we've got the statement at the bottom. It is about 0, right? The base case is 0. We do a substitution to turn the 0 into an arbitrary free variable x. And then we apply the right reduction rule, the right quantifier rule. And on the left-hand side, this becomes, well, we have a of x inside gamma x, so this becomes an initial sequent. And on the right-hand side now, instead of proving that a holds for all y at least x, we need to show that a holds for all y at least the successor of x. Well, I'm not going to give the between steps, but a little bit of logical reasoning about this, about the formulas in gamma x, will actually allow us to, will naturally turn that into a statement. If gamma of the successor of x implies what we want, and then what we do is another substitution where we replace all occurrences of successor of x with x. And now we're at the same point that we were next to the conclusion. And so the natural proof search for this would then continue ad infinitum in this loop. And what we've done is given an ill-founded derivation of the induction axiom without assuming any complex arithmetic. And this will actually be an ill-founded proof in our calculus. And the reason being is that that there is going to be a trace on the right-hand side, which always sees this universal quantifier and does so infinitely often. And in case of LTL, we said that we have to see this always operator infinitely often, and in the case of arithmetic, we have to see the for all quantifier infinitely often. And so we can give a definition of an ill-founded proof in arithmetic. We take the same definitions as before. A trace is a sequence of formulas following the breakdown of formulas throughout a proof. And we have, for instance, following the right-hand formula is a trace, and also we have traces within these gammas. And in the example, I won't read it out, but we've got a formula, we've got a trace that follows through the gammas, and on the left hand we have a trace that follows the for all y quantifier. Let's just put it the universal quantifier on the right. We've got an example of a left trace and we have an example of a right trace. And a good trace is a right trace which is infinite and is principal in the universal quantifier rule infinitely often. An ill-founded proof is a derivation in which every infinite branch carries a good trace, and a cyclic proof is a periodic one. So our proof search for induction, for example, is giving us a cyclic proof because the sequent at the top right is identical to the one below, and we just said, and now cycle. So we have our definition. We had, this gives rise to two new notions of provability. Turnstile infinity says provability with an ill-founded proof without cut. Right. Just for technical reasons, we'll say without cut. And the cyclic provability is turnstile circle, provability with cyclic proof with cut. There's going to be a slight difference here. So the ill-founded calculus, we will not allow cut, but for cyclic proofs, we do allow cut. And the two theorems stand out here. The class of ill-founded proofs is sound and complete for the standard model. That is, that the sequence that are true in the standard model of arithmetic is precisely those that have ill-founded proofs. Soundness, we can prove quite directly. Completeness is actually by proof search, using the same proof search method we described. The second result is something much more striking than the first theorem. And this was a result by Alex Simpson in 2018, that the class of cyclic proofs is equivalent to piano arithmetic. The ill-founded proofs is all of true arithmetic, and the cyclic proofs is piano arithmetic. So a sequence is provable in cyclic arithmetic. A sequence is provable in cyclic arithmetic if and only is provable in piano arithmetic. And in fact, the correspondence here goes quite deep, and Anupam has some very nice results, say, relating cyclic proofs to even fragments of piano arithmetic. But what I want to do here is just show the contrast between these two. Ill-founded proofs gives us true arithmetic, whereas the cyclic proofs give us piano arithmetic. And we can also talk about the cut rule of this. So the reason I formulated the ill-founded proof system without cut is that the completeness result is by proof search and doesn't use cut. And secondly, we are interested also in removing cuts. So the cut rule is admissible in the ill-founded system. How do we prove this? Well, we're going to use the same 3 steps as before. First of all, we need to add reduction rules for the new concepts. That's a spelling mistake. Also concepts. So the reduction rules corresponding to universal quantification and the equality axioms. And, well, if we look at the universal quantifiers, they have precisely the same structure as the always rule does in linear temporal logic. So our reductions for these, we've already given them, just in a different language. Now we've got local reductions. Now we want to apply continuous cut elimination. Well, continuous cut elimination does not care about whether we're talking about modal logic or arithmetic. It simply says, if you give enough local proof transformations, you get continuous cut elimination. So now we know that derivations containing cut, ill-founded derivations containing cut, give rise to ill-founded derivations that don't contain cut. Now comes the tricky bit. We want to prove that cut elimination preserves being a proof. So if we start with an ill-founded proof and we perform continuous cut elimination, we get an ill-founded proof afterwards. So this is what we did in the case of LTL. We started with this kind of proof object. We've got a cut at the bottom. We have certain kinds of infinite traces on the left, and they get matched up with infinite traces on the right side of the other premise. And now we're going to do something really cheeky. We're going to say that we've got our case of LTL. What if we think of LTL actually as a special case of arithmetic? And if we say that the always A means for all y greater than or equal to A, for all y greater or equal to x, and next always means for all y greater than or equal to the successor of x. And then next A, though actually we don't use it in this figure, Next A is then just saying A holds of the successor. And when we think of this, we actually see that what we're doing in cut elimination for arithmetic is exactly the same as what's happening in cut elimination for linear temporal logic. And the only difference is the vocabulary, i.e. the formulas. But the same thing happens, the process does exactly the same thing to traces in this proof. And so actually we get that cut elimination preserves ill-founded proofhood by the same argument as we had for LTL. We don't need any complex arithmetic to find these traces. We already did the work in just studying a simple modal logic. And now what is worth just remarking now is that there's a strong distinction between cuts in cyclic proofs and cuts in ill-founded proofs. The cut rule is admissible in the ill-founded proofs, but it is not admissible in cyclic proofs. That is, that if we have a cyclic proof with cut, we can eliminate the cut, but what we will get is an ill-founded proof and not usually a cyclic proof. And this fact is, well, one way to say it's Gödel's second incompleteness again, but there are some other ways of presenting this observation. So now what we've done is we've studied linear temporal logic, we've studied arithmetic, and actually from the co-inductive proof theory of them turns out to be the same. It was really just, the only difference was the notion of formula, really. Okay, so now let's move to the last part where I want to talk a bit about the theory of this, or the proof theory of ill-founded proofs. And this is quite a young field. We have a lot of individual analyses of these things, but there's not much that is of a uniform or very general argument. So this area is ripe for young minds to come in and see the connections that us old people are now forgetting. So, but let's say a little bit about this. Okay, so there is a way in which we can talk about the complexity of ill-founded proofs. And this is not by looking at the size of them. Ultimately, we have no good measure of comparing the size of one ill-founded proof to another. But we can look at the complexity of cuts that occur in ill-founded proofs. What we say is that we had a notion of trace. Now we're going to say a very specific thing. So cut trace. So a formula that starts at a cut formula, and a trace that starts at a cut formula will be called a cut trace. And we're also interested in the ones that more or less preserve the formula rank, i.e. that they don't jump to significantly less complex formulas. And now we look at branches in an ill-founded proof. So if B0 and B1 are branches in an ill-founded proof, we say that B0 is to the left of B1 if the two branches are split at a cut. So there's a cut and we have B0 on the left and we have B1 on the right. And these two paths, these two branches share a cut trace. They both have there's a single trace, which is a trace on the left side on one of them and a trace on the right side, and they both come from the cut formula. And this ordering is this left-off ordering. It's a partial order, well, okay, the transitive closure of this ordering is a partial order, and it's well founded because we're just always moving left in a proof, so it must be well founded. So we can talk about the rank of this, and we take the rank of a derivation, of an ill-founded derivation, to be the order type of the left-off, this special left-off relation. And then what it turns out that one can prove that if you have transfinite induction up to the rank of an ill-founded proof, then you can eliminate the most complex cuts in pi and prove that the result is an ill-founded proof. So preservation of proofhood is, or can be reduced to talking about transfinite induction along this rank. And the result I refer to here is trying to work with Bahari Afshari, and it's currently unpublished, but it's under review, but it's available if anyone would like to read. And the claim is that over a certain subsystem of second order logic, transfinite induction up to the rank of a proof is sufficient to show that continuous cut elimination, one pass continuous cut elimination, preserves being a proof. Our conjecture is that a weak system of second order logic is sufficient. This is the theory of Weak-Koning's lemma. That is definitely, we can't go lower down than that, but our conjecture is that that suffices. A more hedging one's bets a bit, at least the theory of ACA 0 should suffice for this. Okay, so in that theorem there are a few caveats, because suddenly I'm talking about ill-founded proofs in general, but I'm not saying what kind of sequent calculi are we working with, so do keep that in mind. But the theorem of cut admissibility for arithmetic that I presented already fits in this theorem, and indeed it can be generalized to also include intuitionistic theories of higher order induction. It seems to be more complex to allow to look at classical logic theories in general, but for the intuitionistic fragment, this analysis turns out to work quite well. Okay, and actually now I'm wrapping up, so let's return to the ordinal analysis of Peano arithmetic. Can we get the classical ordinal analysis of Peano arithmetic that says that induction up to epsilon 0 is sufficient to prove the consistency of Peano arithmetic, or some other characterization of Peano arithmetic with epsilon 0? Well, we can get it by our theorem, or the conjecture, if one other property holds, and that is that if we can bound what happens to the rank of derivations through continuous cut elimination. So if pi is an ill-founded proof and it reduces to rho by one process of continuous cut elimination, then we would like to know that the rank of rho is bounded by, well, some polynomial in pi. I've written here omega to the pi. This is not, it is not known as far as I'm aware, but if this holds, which is, I would say, is not an unreasonable property, but if it holds, then we would have another proof of the fact that the consistency of Peano arithmetic can be proven in this case, Weak-Koning's lemma plus transfinite induction up to epsilon 0. And in this case, without needing any hidden use of recursiveness. the recursiveness of the properties is all of the proofs is all implicit in the continuous cut elimination and in the formalization, but we don't need to have two notions of omega proof, the general omega proof and the very special one for proof theoretic analysis. But then, and this, let me finish with one general question for anyone that wants to start working in this field. Is this one, I mean, even this result of time claiming has not been established, but on its basis, is there really a general theory, a general method of proof theoretic analysis that we can apply to many theories beyond arithmetic using other inductive concepts? Theories of truth, theories of second order logic themselves, where we actually give a very general argument which just uses this principle of continuous cut elimination and observations about cut rank of ill-founded proofs. Okay, so now I'm done. So thank you very much for your attention.
Okay, let's first thank the speaker, Professor Grant Leigh, for this very wonderful and inspiring lecture. Okay. Yeah, it's a start from basic proof theory and then introduced ill-founded proof. It's ideal, detail its application. Okay, we still have some time. Okay, and now let's welcome Professor Anupam Das. He's the commentator for possible comment or questions. Please.
Thank you. Can you hear me?
Yes.
Yeah. Yes.
Okay, cool. So my connection's a bit iffy, so let me know if you don't. So first, thank you, Graham, for a really, really wonderful lecture. I really enjoyed the story that you told, and in particular, seeing the stuff that you've been working on towards the end. I'll go a little bit reverse chronologically because I'm quite interested in the stuff at the end. And the question you put at the end, I find quite interesting. So your presentation of cyclic arithmetic is based on this idea that we can see the quantifiers as fixed points in a sense. And so, of course, by extending that idea, you get some kind of reduction from, say, arithmetic with even general fixed points to just a propositional system with fixed points.
Yeah. At least informally, yes.
No, but I think using the embedding of quantifiers, then you commute with even other fixed points, right?
Yes, I guess yeah. I suppose it could. Yeah.
But so the question is, are you confident that the methods you're talking about might be useful for analyzing such a theory like that? Because that would give you that's a much more powerful order analysis.
So what kind of theory did you mean?
So imagine you have like PA with general inductive definitions. So like
general inductive.
Right, and then carry out a translation like the one you did of the quantifiers, but also commute through further Muse and uses. You already have fixed points. So if your techniques were general enough, then you could also get consistency proof for much, much stronger theories.
Yes. Okay, so that is interesting. So I only thought about this connection between the propositional and the first order case while I was preparing this talk, actually. And I wanted to do the more complex case by analogy, and then it turned out it was actually more than by analogy. But I think that's a really fascinating possibility. That for a start, that one can do an analysis of arithmetic by projecting into a simpler language, a propositional language, essentially, and that has a lot of benefit for reasoning, certainly. Yeah, so I think that's possible. As for generalized inductive definitions, yes. So the argument I presented here already works for beyond arithmetic. One just needs to know how one should treat the notion of rank for generalized inductive definitions. If you've provided these inductive definitions as stratified, so it's not a Mu calculus, but an ID system, the cut elimination process will go through for classical logic. Yeah.
I see. So the preservation of progress argument is general enough for non-interleaved inductive definitions, but
Exactly, yeah.
Okay,
It's all about finding these threads or proving that those threads are, first of all, exist and that are preserved through the cut elimination. And that is where we leverage on these inductive definitions with this non-interleaved form.
I suspect I guess you suspect that it will be a lot more complicated with interleaved inductive definitions, because now the mapping from branches to branches can become quite complex.
It can become very complex. So
you have some kind of game semantic interaction or something at that point.
I mean, we've got people here working on that, but that's a long way for general. I mean, it turns out to be a logic thing. So things work this way. Things work quite well in an intuitionistic fragment. The traces are much more robust under the transformations are more robust under traces, but for classical logic, all sorts of weird things can happen with traces. Interacting with one another across a cut.
Oh, I wouldn't have guessed that the base would have made a difference. Can't you factor the classical case through the intuitionistic case and some sort of double negation translation?
So what the result that we have that I didn't mention here is that for higher order fixed point logic or higher order Mu calculus with strictly positive fixed points.
Strictly positive. So the double negation will destroy the strict positivity.
Exactly. Yeah. But for stratified, one can use a slightly different argument, which is more in lines of what I was sketching in this talk.
Okay. So then, still on this final part of your lecture, you talked about the formalization in second order arithmetic. And I think one thing that wasn't clear to me is exactly how you're carrying through the statement of progress during the one single pass cut elimination. So are you proving an analytical statement here, where you're saying, if every branch has a progressing trace before cut reductions, then every branch has a progressing trace after cut reductions?
So what you do is relate the branches of the new proof back to the old one. So they ultimately say that every branch in the new derivation is the amalgamation of a certain collection of branches in the starting derivation.
Like
and that's the property. Sorry?
Like a cut subtree.
Yes, yeah. And yes. So that's exactly the kind of observations that have gone on before in other work, but that's of a lower complexity, as it were. It's a relationship that you can get as a that you can carry out through the process, and then as a corollary of that, you get preservation of proofhood by seeing that every such cut tree must have a good trace that is witnessed in the new one.
So maybe what I'm trying to pinpoint is that final step, you don't need to use any extraneous set existence principle to get the progressing trace, because you're saying you're working WKL0, right? So you have very little set existence.
Yeah. Okay. So the WKL0 is a conjecture, so we have not looked closely at what we really use for sure. But yes, the claim is that it doesn't involve a set existence, Emma. It is about tracking concrete things. I mean, they're infinite traces, but they're concrete when you're in the starting proof.
I see.
And
Okay,
it's
so then
the
maybe a final
transfinite
question.
recursion that's
Say again?
doing. It's the transfinite recursion that is doing the work on finding the right kinds of threads.
Okay. So maybe I've got one final question on this part, and then I'll maybe move to some more high-level things that maybe of more general interest. So just how, so this argument you presented, is it sensitive to the presentation of cyclic arithmetic that you showed us? Or is it, can one recover it for, say, Simpson's original presentation by factoring through some translation?
In some respects, it is sensitive. I should think that the Simpson argument is not far away from this approach. So, I mean, the Simpson calculus. I think you should be able to get it to work for the Simpson calculus, but I always find that calculus a little difficult with respect to what a trace is.
Okay, so maybe instead, maybe you just have like a single inductive definition for natural numbers.
Yeah. So then you could do it that way. Yeah. You could do it that way, but the advantage of using the quantifiers as inductive definitions is that first order quantification is ridiculously complex. I don't want first order quantification as in the sequent calculus when I'm doing my cut elimination. Essentially, I want this modalized form, and it keeps the traces nicely behaved. Yeah.
So okay, so I've got some other questions that maybe I'll take offline for the interest of the audience. So wait, so Yong, should I keep going with questions, or do we open up to the audience?
Yeah, if you have more questions, yeah, please take your time. Yeah.
Okay, cool. I would love to keep going. And so, Graham, I've got a few high-level questions here. So, so thank you for pointing out this apparent paradox of, we use all this ordinal complexity to prove cut elimination, and in fact, just if we have a big oracle, then proof search is very easy, which is a phenomenon we see all across proof theory. The differences between cut-free completeness and cut elimination. And so, did anyone study things in between? Do you know? So we know that something like PRA plus transfinite recursion up to epsilon 0 can prove that any proof omega proof can be transformed into an omega proof of height less than epsilon 0.
Yeah.
Right, the original proof is relatively low in height. And we know that if we take PRA plus, I think you can formulate this plus some truth predicates, then I think you can formulate the fact that if it's provable, well, then it's true. And if it's true, then it has a cut-free proof of height bounded by omega squared. So what about PRA plus statements that from any low height proof, there is a cut-free proof of height alpha, where alpha is somewhere between omega squared and epsilon 0?
I have no idea. No idea about that. So yeah, I've never seen that kind of statement. I wouldn't know where to start. So, okay, that's curious. I'd have to think about that. What it would mean. As to your the kind of the starting part of this question, there's not really anything in between that has been of proof theoretic interest. So you've got the two extremes. You've got the general omega rule, which does have a role in proof theory because if you work in a system like of inductive definitions or set theoretic system, you reason about the full omega rule, but it's the omega rule internalized in the system. But if you're working with respect to systems of arithmetic where you need to code proofs, you need to have some way of coding them, and recursive, and in fact primitive recursive is all you need for these omega proofs. Something in between I've not seen, and the same question goes for ill-founded proofs. So we've got cyclic proofs, we've got ill-founded proofs in general. What classes of ill-founded proofs are of interest? Certainly the recursive ones have some interest. What about other notions of other complexity classes, and
Mhm.
I don't know. And then there may of course be a relationship. That there probably is some kind of relationship between the complexity of omega rules and ill-founded
Oh, right,
proofs.
right. I see. So if you limit yourself to just the recursive, non-well-founded omega, well, even let's go back to omega proofs. If you just limit yourself to the recursive omega proofs, of course, you don't get a completeness argument, right?
Yes. Yeah, that's right.
So do we know about if we restrict ourselves to recursive ones?
Um, well, the domain of recursive omega proofs is the domain of proof theory. So, the, and I mean, and this was also the class that Mintz was doing his continuous cut elimination for originally. So, what was your question then?
I don't, it's just a naive question. Do we? What's like the proof theoretic strength of recursive omega proofs?
Oh, I see. It, one inductive definition, I should think. You need the theory
Right.
of
Yeah, that makes
recursive
sense.
ordinals,
Yeah.
then
Okay.
you've got omega logic. Yeah.
Okay, that makes sense. Okay, and it doesn't even matter. Okay, then actually, okay, that kills my next question as well. Because I suppose it doesn't matter that it's recursive. It could be any arithmetical or even sigma 1 1 then.
Yeah. Then you get different notions of omega provability. So, yeah.
So I want to go up one level again. So you were talking about the activity of proof theory these days, and what we study, and as you rightly say, most of us are looking at cut elimination and trying to see what content it has, either through theoretic means or computational means or whatever. But back in the early days, before Gensen, there were other approaches that sort of died out. So things like the epsilon methods. Um, is this something that in the world of non-founded, in ill-founded proof theory, that we should be looking at? Is there something there for us to say in that area?
I can't answer that, but I think it's well worth a look. So you bring up the epsilon calculus, and I think that's an excellent example. So what happens with the epsilon calculus in this setting of ill-founded proofs? Is it a calculus that fits well with an ill-founded proof? I would guess it does, but I don't know. So it would be worth looking at because part of the motivation behind the epsilon calculus was to streamline the many of the proof theoretic complications with arithmetic.
Mm.
And epsilon calculus does that on a low level, but the proof theory of it becomes very complicated anyway. So it would be
Yeah,
interesting
the
to see
structural proof
whether
theory, the actual
the structural proof, yeah,
Indeed.
yes. So, but possibly, maybe it will turn out that the epsilon calculus is a very natural calculus for ill-founded proofs.
Maybe just to add a comment here, which may even more suggest this. So I think in the original proof theoretic analysis of PA through the epsilon calculus by it was Ackermann, I think. So he actually uses a form of the epsilon operator that picks out the least witness.
Mm-hmm.
And the reason for that is very obvious. It gives you an induction principle by doing so. And so there really could be something to say. So using a substitution method like he used could be something that could be compatible with the methods of inductive or co-inductive proof theory.
I think so. And I think an excellent topic for a PhD thesis. Yeah. I think that, yeah, there's this, and then there's, as you say, there's other approaches that had merit when they were introduced before the Gensen method and didn't achieve what they thought they could achieve, but maybe it was they were suited for a different perspective of provability.
So I think I'm done with questions and comments for now.
Yeah, Anupam, do you have more question, comment? If you have, you can continue. Anyway,
I'm happy to stop now. I think it's a reasonable place to stop.
Oh, okay. Thank Professor Anupam Das for his comment and questions. And the next question is Professor Goran San Ho. Please, I see you raise your hand. Please.
Thank you very much. Thank you, Graham, for this. It's a long time since I was able to understand everything in a mathematical logic talk here, because my very first publication was on the infantry tense logic. And my doctoral dissertation was on Mint's continuous cut elimination. So this was a perfect, it brought back things from 40 years ago to me. But so I've got a couple of comments. First, about the epsilon calculus. I think that is highly likely that interesting things can be done there, since Hilbert's mathematical background for this was the integral equations, right? Generalizing Fredholm's work and so on, right there, so that it is iterating various things, which is what you do, which is very much like defining the solutions of integral equations there. So that I think there's quite strong likelihood that something can be done on that. But then about the omega proofs, one thing I found out, when I did my dissertation, I was very surprised at the differences between the results of choosing various parameters for representing proofs, right? In particular, choosing intuitionistic versus classical logic at the bottom, because the recursive restriction on classical omega proofs is complete. But intuitionistic logic at the bottom, when we add the recursive omega rule to that, does not prove all true formulae. It's got to do with reliability as well, right? And this brings me to the question what you said about the there was something fishy about what you said about the recursive omega proofs of order less than omega square here, because we have got those, even Kalmar elementary, right? If we start with a correct sequence at the bottom and then do proof switch at the top, each step there is Kalmar elementary. And if it stops in the Kalmar elementary proof. But of course, we don't have a proof of its local correctness. We get the Gregorczyk index for this Kalmar elementary function. But to prove that it is locally correct, that is for that we need very strong assumptions. So I think there is no conflict here. But those proofs certainly will have ordinal height less than omega square. But we can't add constructive ordinals and then prove that it has got that height less. So that was also that the recursive omega rule is not complete constructively, but classically it is. And are there more things in here? Yes, it is quite sensitive, of course, that the Mint's use of the repetition rule, you didn't mention that, but that is essential, right? Because that is recursion theoretically, that is the use of a marker. It allows us to make, can we say, march on the same place until enough information crops up. What we need to do is we need to decide Keeney's T predicate by the length of the node where we are. And then as we go on one more step, if we can't yet decide the T predicate, we repeat. And since we know that the function is recursive, sooner or later there will be a suitable witness to plug into the T predicate and decide the question. So that's why when we start with the recursive infinite omega rule, we can replace that by a Kalmar elementary one by stretching it, introducing possibly very, very long sequence of uses of the repetition rule. And that must play a role somewhere in what you are doing as well, I think, such phenomena.
Thank you. Yeah, for those it's a privilege to have such an expert on the omega rule in the audience, Haran. And yes, yeah. And first of all, yes, your comments on the classical recursive omega rule. Yeah, yeah. Now you mention it, it's straightforward. Yes, and the trouble is about the correctness of this. For the Min's repetition rule, so indeed, Min's method, he uses a repetition rule which just says do nothing. I have the premise and it has the same conclusion, and that has a very important role in, but it does not have such an important role in this study, because there the issue was using omega branching proofs, and your code is about a recursive function that gives you the rest of the proof. Here we assume our proofs are described directly as trees, labeled trees. So it depends slightly on what you mean by continuous here. So if we mean continuous with respect to the standard metric continuity, then we do actually need a repetition rule to say that, well, we can decide about an initial segment by looking at a certain initial segment of the input. Yeah. So something like that is needed for continuity, but for the properties we get from continuous cut elimination in this setting, we don't actually need the repetition rule there. If you allow yourself a little non-determinism in the reductions, perhaps. So, and I suspect also you could give a different notion of a different topology, which you don't need the repetition rule, but that's a minor distinction.
Okay, no, but I would not be surprised if what you say here, it makes good sense, since these original choices are very delicate when you got the omega rule. People speak about the omega rule as if everything was crystal clear, but it certainly is not, right? And that you also got, you can't use that here, of course, but when you got omega proofs, you can code that by either Church-Kleene O analogy or by letting the whole proof tree be recursive.
Yes.
And so and then there are various differences between the two, but grosso modo they are equivalent as to approaches, just in the same way that we can deal with ordinals either using recursive well orderings or the Church-Kleene O notations for that.
Mm-hmm.
But there certainly are differences. So thank you.
One can embed the omega rule into the ill-founded proof by just an infinite case distinction. So certainly one can have the same kind of complexity theoretic issues or interests from omega proofs in this setting, but somewhat ignoring that, because you don't need your proof to be encoded in a specific way. It's helps.
There was one thing I couldn't do in my dissertation that I've been wanting to have ever since, right? Because the backward search in the classical case gives a canonical tree that is uniform in the Gödel number of the sequent at the bottom, right? And if that is true, it stops then in a well-founded omega derivation. Provably, we can't have such a canonical tree, uniform one, in the intentionistic case, because it depends only on the sequent, and that would mean that we could realize unrealizable formulae in Kleene sense, because of the recursion theoretic uniformity, so that we can't have. But there is, of course, an enormous amount of information in the backward search, recursion theoretically, also in the intentionistic case. And I had hopes that by asking finitely many non-effective questions about the branches there, and then cutting off what one didn't want, we would get, nevertheless, not uniformly in the sequence, but by asking these illicit questions, so to say, you would nevertheless get the recursive Vega proof. But I never, it would be something like a priority arguments in recursion theory, right? But I wasn't good enough a mathematician to get that done. And there is nothing known on this score here, how to deal with. So it's remarkable that the difference between the classical and the intuitionistic case is so great, right? Because the double negation interpretation holds, but nevertheless, it messes things up.
I think the moral is that the omega rule is not as robust as it looks.
On the contrary. Okay, but thank you very much for that. Simpson, 2018. Is it Stephen Simpson? I looked for the paper.
Alex Simpson.
Sorry?
Alex Simpson.
Ah.
I
okay,
might have the year out by one, but
where was it published?
in the conference FOSSIX. So I can't remember what that
Okay, yeah, but then I can find it.
Yeah, the title. Ruben is in the audience and he's put it in the chat. FOSSIX 2018 or 2017.
Okay, Anupad, do you have any follow-up? I see you have you post your personal message. Yeah.
No, I was enjoying the interaction between Goran and Graham. But I think maybe just had a point of view that may clarify some things. Is that I think this issue of whether you use the repetitions or not, to me, it's a bit of a red herring. So by all means, you can use the repetitions and you get continuity in the standard topology, as Graham says. But of course, the harder thing is just verifying that progress is preserved. Once you have that, you can safely delete any repetitions. It's a corollary, a much weaker corollary of that. That the thing you obtained after continuous concatenation is topologically correct.